Now, for 3 dimension, in fact, this should be written in this way. F is a vector, and then dot dx. Dx is a vector, okay? But it's a differential vector. It's a very small change in the vector x, and then you integrate it. How do we understand this kind of expression? Okay, so far you only learned this one, and this one, in fact, you can expand it formally in terms of the vector notation. Think about this one. Actually, okay, if this has a vector here, it's actually a 3-dimensional quantity. So usually for 3-dimensional quantity, we call it R. Okay. So it can be expanded like this. We know that if we have A dash B, it can be written as AX BX plus AY BY plus AZ BZ, right? Okay, this is inner product. So here, similarly, you can write this as F, so it's Fx multiplied by dx plus Fx multiplied by Fy multiplied by dy plus Fz multiplied by dz. But you have integral, so you put integral here, and integral here. So actually you can see that you just integrate it along x direction, fx dx, along y direction and z direction, and then add them together. Okay. So again, it's just a normal process of vector decomposition. So you get fx, fy, fz, and integrate them separately to get add them together.
What's that on top of it? F dot.
F vector dot dr vector. Okay. So this is a formal expression that are equivalent to each other. So of course, if you get the x, y, z component, you can do this evaluation. Question?
What would be the new equation after you integrate? After you integrate the w equals f times dx, what would be the new equation after you integrate it?
After I integrate it, you mean this one?
No, the one that you just wrote out.
This one?
Yes.
I mean, this equals to the integral, right?
Right.
So all this is will give you the work in 3 dimensions. Okay. I didn't do any separate integration. It's derived from the original definition of the work, the definite integral here. Okay. So this is just the work along x direction. This is the work along y direction. This is the work along z direction. And we put them together. And these things together will give you delta k. So this is a work along 3 dimensions. If it's a variable force, how can you integrate it? Okay. So for example, if I give you some force in the vector form, I cap, j cap, z cap, okay, something like that, and I ask you to calculate the work, can you do that? So you need to know how to do that. Okay. So for example, let's say force, any particular force, let's say equals to 2 I cap plus 3 j cap plus 4 z cap k cap. Okay, if that's a force, if I integrate it, so the work would be fx, which is 2 integrate dx, plus fy, which is 3 dy plus 4 dz. Okay, and here, of course, each of them you have your initial position x naught, initial, x final, and y initial, y final, z initial, z final. Okay, so it will give you this kind of integral. Okay. So now let's look at one example. A spring. This is the variable force, but we can go back to the one-dimensional situation. Okay. The spring force is given by the Hooke's law. Fs equals to negative kd. Okay. Fs equals to negative kd. Precisely speaking, it can be along any direction, but this is a one-dimensional force, so you can just choose the direction along the x direction. So let's try to evaluate the work. So the work in one dimension is just F S multiplied by dx from the initial position, x initial, to the final position, x final. Okay. And Fs equals to negative kx. Okay. If we make this along x direction, so we get Fs equals to negative kx. Okay. Dx, x initial to x final. So of course you can factor out negative k. You get x initial, x final, x dx. And we know how to integrate the x dx, right? This is 1/2 x squared, right? So you get negative k 1/2 x squared, x initial to x final. So this will give you negative 1/2 k x final squared minus 1/2 k x initial squared. Okay? K is constant. K is called the spring constant. It's a quantity to characterize the stiffness of the spring. Okay, a hard spring will have a larger K. So it's just a constant for a spring. So you can factor it out. So of course, then this one, we know this has to be written as negative U final subtract U initial. So we can identify that the spring potential energy can be written as 1/2 k x squared. Okay? This is the spring potential energy. Again, the integral is a way to relate everything here. I want to emphasize. In some previous class, we have to memorize this definition, okay, separately. We say that spring potential energy always 1/2 k x squared. But you can see this is just the direct result of the force. Okay, if you integrate it, you get the work. Any question here? So when you started calculus physics, you have less stuff to memorize. Basically, if you really understand everything, the only thing you need to memorize is just Newton's second law and the definition of several forces. All other things are actually, we always integrate it or take the derivative to get those things. Question?
Wouldn't that US formula be negative?
This negative comes from this negative. Right?
So when you rewrote it over there, as US is equal to 1/2 kx squared.
Okay, here please note that W equals to negative delta U. So I have to leave the negative side in front of them to get the definition of U final and U initial. So there we have W equals to negative this. This is U final. This is U initial. So this negative side sometimes can be a troublesome to us, but you need to remember, you always need to put the negative side in front of delta U to relate it to the work in the calculator. But fortunately, these things will only, in fact, W equals to negative U, negative delta U, or delta U equals to negative W. This equation, we only need to use it when I try to look at the, try to derive the definition of the potential energy. After we got this expression, okay, we can simply use delta U instead of WC. So we don't really need to use these two equations when we solve the problem. These equations, okay, because we are going to replace. The basic idea is that we want to replace WC by delta U.